Hey, Andrew McLaren here. We're going to be doing limiting reactants. I remember this was one of my most common and also one of my most favorite things to tutor people on because it's something that conceptually isn't very hard, but there's a fair amount of math, and you just need to learn how to keep track of the math and think through it. So to help us do that, what we're going to start with is thinking about what it really means to limit a reaction. And then we're going to think about some analogies to help you understand that a little bit better. Then we're going to visualize what we're doing with limiting a reaction with some bar graphs so that you kind of know what we're aiming for. And then we'll actually do some calculations. But I really want you to not just be able to identify this limiting reactant, but be able to understand models around it, because then you'll be able to double check your work. And if you can solve for one part of a problem, you should be able to solve for all the parts of the problem. And they typically ask for like two or three different stages with these. So it's really important to not just be able to find a number, but know what that number is. Okay, so let's get to it. Let's start with a classic example of a limiting reactant. So these are two chemicals that you can mix together relatively easily at home. They're two cleaning chemicals. Don't do that without parent supervision, though. Um, but basically, if you have baking soda, which is a solid, and you have some vinegar, and you mix the two of them together, you'll get some gas produced, carbon dioxide. There will also be some water and some ions still in that water. But what we're interested in is this gas production. And this is commonly used as an example of limiting reactants. So people will typically set up like five or so flasks and they'll put different amounts of the stuff in and see how much gas is produced. So without any math or understanding of limiting reactants, I was able to work through this concept with middle school students and they totally understood the big picture. So don't worry, you got this. Not saying that if you're not getting it, that's bad, because I've also met plenty of high schoolers who struggle with this stuff. Basically, what we have here is there was a certain amount of vinegar that was in there, 70 milliliters. That was the liquid. And then we put in different amounts of solid into the different beakers. And you can see that the final volume of gas produced did get bigger, but then it stopped getting bigger after a certain point. So this reaction was limited. But the question is, what was it limited by? And so you can see that this was a constant right here. We just had this was constant. And then we had this was increasing. So we had the solid was increasing. And basically, it seems that in this point that they both were able to react as much as they could. And then it doesn't really matter if you add more solid because we have used up all of the other reactant. So we've used up this one, the aqueous, in this first situation. So it was what was limited, limiting the reaction. So this was limited uh, by the what was constant, limited by the aqueous. So that's the vinegar or the acetic acid. So we can also set up the same sort of lab, but tweak it slightly. So now that we've got the same amount of solid and we have different amounts of liquid. And so you can see in this situation, we're going to be limited again right here. And that was because we had this, which was now increasing, and the other one, which was constant across our different experiments. And so in this, you can see, okay, yeah, there was the solid here, and we had different amounts of the liquid. It doesn't seem to matter if you add in more of the liquid here because we've essentially used up all of the solid. And if you do this, you can actually see that there isn't any solid left up. left over. And so in this case, we're limited by not the vinegar, but we're limited by the solid, by the baking soda. If we can't go any further than that, right? So like all of this was limited by that that baking soda right here. And same thing, all of this was limited from there on out by that vinegar. It doesn't matter if you've got more of the doesn't matter if you've got more of the solid here, we're limited by that vinegar. Now you can look at the moments from beforehand and you could say, okay, well this, we probably had too much vinegar, and so this was actually limited by the baking soda. And then by extension, this is also limited by probably us having a little bit more of the vinegar than we need, right? Wait, is that right? Let me just double check that. Yes, that is right, because in this situation we had excess vinegar, so we didn't quite have enough baking soda there. Yeah, okay. So that does actually make sense. So this is the limited by the vinegar. Okay, all right, next part. Analogies are really, really useful for understanding limiting reactants because it's kind of hard to understand molecules and whatnot, but it's very easy to understand like making a sandwich and running out of ingredients for that. So there's a couple simulations that we're going to look at to help us, and then there's this little example with some numbers that we're going to use as our analogy. So if we have some sort of reaction, and don't worry, I'm going to do a whole video on balancing reactions, but you can think of it as like having some reactants on one side and products on the other. And we need to make sure there's an equal amount of the mass on the two sides. And so you can see when I've got these numbers here that I've got even amounts of nitrogen and hydrogen on the two sides, so that this reaction is balanced. And so when we have a balanced reaction, it essentially is like a recipe list. Like you can think of this as ingredients, and this is like a product. Like if you have nitrogen and hydrogen, you can put them together and make ammonia. You can do that with all kinds of reactions. Basically, this idea is that we need to have the same amount of the two things on the two sides, and you can make the product from the reactants, in this case where they're splitting up water. So there's a very simple analogy of like making a sandwich, and you've got different amounts of ingredients. And in this simulation, you can see like, okay, well, I've got different amounts of reactants, and that will make some product. So right here, I can make one sandwich because I've got 2 pieces of bread and 1 cheese. You can see the reaction right there. Here, we're just working with number of pieces of bread, but you could also say if I've got 2 packets of bread that each have dozen pieces of bread in it, and 1 packet of cheese that also has a dozen pieces of cheese in it, then I can make 1 dozen sandwiches. That's basically what we do with molecules and moles, because the mole is just like a really big, like I call it the chemist's dozen instead of baker's dozen of molecules. So that's kind of what we're doing here. But for the analogies point, we're just kind of thinking about like the individual units, like bread and cheese. It's typically how we think about it. So I can have more bread, but in this case, I'm being limited by the amount of cheese. And then I can change this up, and now I've got tons of cheese, and I'm being limited by the amount of bread that I have. So the amount of product is being limited by the amount of reactant. So our real objective with the limiting reactant is to figure out which one do we really have less of, depending on also the reaction, because I can have a little bit less cheese than bread, but I'm still uh, being limited by the bread because I need more bread to make the sandwich. So it's not just the amount of the reactants, it depends on how much you're putting into the reaction. And it also typically they don't give you like molecules, they give you the weight. And so imagine if I gave you like weights of bread or cheese and I said, how many sandwiches could you make from that? That's basically what we're doing with the limiting reactant problem is that we're given some weights of these things and we're asking how much product can we make, typically also in weight. So it's kind of weird. But that's the idea. So you can also imagine if I have a different reaction, I'm going to have different limiting reactants. So I can have like a nice balanced reaction there, or I could have it limited by my bread. I've got more meat and cheese to make plenty of product, but I'm still being limited by my bread. So that would be my limiting reactant in this analogy. So if I had, it's kind of weird to think about. Someone wouldn't really tell you like you have 500 grams of sliced cheese, but let's say um, that like 50 grams of cheese is equal to one slice of cheese. And we're going to do the same thing with like the bologna. Let's say that maybe 25 grams of bologna is equal to one slice of bologna. And then let's say 50 grams of bread is equal to one slice of bread. So we have some amount of mass. We now need to figure out how many of these things we have. Also, keep in mind how many of them we need in the recipe, and that should tell us how many sandwiches that we could make. So if I had, let's say, I've got I'm just gonna bring it over here so I got a little more space. Let's say we've got the 500 grams of cheese. I'm just gonna do C for cheese. And I can say 50 grams of cheese is going to be one slice of C. And it's also important to keep in mind that we're not just asking how much slices of cheese we have, we're asking how much bread we can make with that, or how many sandwiches we could make with that. So let's say one slice of C, that's going to be equal to one sandwich. And so we can do that. Multiplication, this would be 10 slices. So we have 10 slices of cheese. So we should be able to make 10 sandwiches. I'm just going to do S for that, just to mark the sandwich. Same thing with the 250 grams of bologna. We can say that one slice of bologna is equal to 25 grams. And we only need one slice of bologna for one sandwich. You can probably see how where this is going. This is also going to be 10 sandwiches. And then we've got that, I think it was 1,000 grams of bread. And yes, I chose easy numbers on purpose. It just makes our lives easier. And we said that 50 grams of bread was equal to one slice of bread. And this is where it's important to keep in mind how many of these things go into a sandwich, because 2 slices of bread are needed for the sandwich. And so if we do that, 1000 divided by 50 divided by 2, that should also be 10 sandwiches. So in this situation, we were able to make 10 sandwiches, and there wasn't really any one thing limiting the reaction. All of them were limiting reactants. They were all equally limiting in how much product could be made. You could imagine, let's say maybe I had like 500 grams of bread. Then I've only got enough bread to make 5 sandwiches. And so the bread would be the limiting reactant in that situation. But in this situation, there wasn't really a limiting reactant with the amount of masses that we had. This is kind of analogous to when we had exactly the right amount of baking soda and vinegar, when they were perfectly reacting and making as much product as both of them could make. That's kind of like what happened here. Okay, next part, yeah? Okay, I know that you're looking at a lot in front of you. Give me a minute to kind of go over this, and it should really help you in understanding how to find a particular thing that someone's looking for. So I started off with these black boxes just showing a rough amount of mass of some reactants, A and B. So you can imagine that you've got a lot of A and a little bit of B in terms of what you weigh on the scale. And then you let them react, and you have absolutely no A left over. It's all turned into C and D. There's a little bit of B left over. We can call that the excess. So oftentimes people will ask for how much excess of the second reactant do we have. And so that I just wanted to help you kind of visualize what we're looking for in that regard. Like in this case, all of A has been used, a little bit of B has been used, but not all of it. So there's some excess. And then there's some amount of product that's produced. It might be D that you're looking at. You might also calculate how much of C you have left over. And this is usually like they're giving you some mass and asking for some mass. So that's kind of what we're really working with in the beginning and end, but we're working it through the moles. So moles are kind of like your slices of cheese, and the mass is that grams. Like we can't really work with that. We need to know how many pieces of cheese we have. We need to know how many molecules we have. And so we work with moles when we're trying to do something like analogous to molecules, because if you've got twice as many moles, you've got twice as many molecules. Like it's a really big number, but if I said you had 2,000, that's twice as much as 1,000. Or if I said you had 2 million, that's the same as saying you've got twice as much as 1 million. So it's the same sort of idea with moles. And this is basically how I do my problems, is I think through how much have I taken, and I think through and label initial and used and excess. That's what I found helps students the most with these problems, is just labeling what is initial, what is final, what was used, what is excess. Also making sure that you're labeling out the, it's really important to label out the units and what the units are of. So like the molecule that you're working with. And what I did was I chose to do this reaction. We've got 2 iron reacting with 3 water, and we get an iron oxide and some hydrogen gas produced. And the reason I picked that was because I know that iron is a fair amount heavier than water. And so I know that iron's going to weigh a good amount compared to water, but it may not actually have more molecules. So I was trying to think through a problem where like maybe you have only 2 moles of water, but 5 moles of 5 moles of water, 2 moles of iron, and try and figure out how much we can produce. So I'm just going to walk through that, and then we'll also do some calculations. So in this situation, we can say how many moles of iron are going to be needed to make some moles of iron oxide. And so if we look at the reaction, we have a 2-to-1 ratio, and that kind of makes sense. It needs 2 iron uh, in the iron oxide. So you're going to use up 2-to-1 ratio, right? So if you have 2 moles of iron, you're going to be able to make 1 mole uh, of the iron oxide is produced. And then if we had 5 moles of water, what you can say is that the water has a ratio with the iron oxide. You can get that from the reaction. This is kind of like the recipe for making the sandwich. You can think of these as like sandwiches and these as like ingredients for making that sandwich. So it looks like we need 3 for every one of those, right? So if we look here, we can say that I need 3 of the O2, or of just H2O. I think it was moles of H2O to every one of these. And it's super easy to accidentally flip these numbers. That's why I write in the, not just the units, but what the units are of. Very, very important with these types of problems. So 5 divided by 3, that's like what, 1 2/3, or 1.6 mole of the iron 2 oxide produced. And so what we can see is that this could produce, like if we had 5 moles of water, we could produce more of this stuff than if we've got 2 moles of iron. And that's kind of what I was thinking through here. Like you're gonna start with the one that's limiting. So this, we can see that this right here is limited by the iron in this situation where we're starting with the 2 moles of iron. Usually they're going to give it to you in grams. So we could work through that, but I also wanted to just show you the kind of in reference to this. So we've used up some amount of these 2 things when we do that. And so you can also calculate, really this is not what's produced. This is what was possible. And so you can say like there was a difference of this in 0.6. So this has the potential to make 0.6 more, right? Like it's got some B still that could be used to make some more of that stuff. Okay. And then, yeah, there's a million ways to go back and find these other numbers and see, okay, how much of this B do I actually have left over? You could say like, okay, what if I had 0.6 mole of FeO3? So this is what's possible. You can think of this as what was possible, and you can go ahead and go backwards and say, okay, well, I've got just the reverse of this. We can do that on top, this on bottom, and that will tell you how much you have left over. And so in this case, it would actually be 2 mole H2O, and this was what was in excess. And so we've got that excess amount there, which kind of makes sense because I think we said we started with 5 and then we're going to end up using 3. So we're left over with that 2. And you could also get this straight up from our 2 moles here, I believe. You could also do like the 2 mole of Fe, and then this is going to react some mole of Fe to some mole amount of water. And you could say, okay, well, in this reaction, I'm going to have a 3-to-2 ratio, right? And so I can say, okay, I'm going to use up 2 of these for every 3 of these. And that this is, let's say this is what's used. And then you're going to end up calculating through that conversion. You've got 3 mole of H2O, which was also used. So you can see this is really important to not just be able to do dimensional analysis, but be able to identify what it is in the problem. So this was, okay, I was using up 2 of these moles. How many of these moles am I going to be using up? Well, I'm using up 3. So it's important to think through, okay, what's kind of decreasing, how much is it decreasing, and what can I figure out from that by relating that? And it's really common for them to ask you how much is left over of a reactant. So you are going to need to be able to do this stuff. So in addition to what we just did with the moles, you're going to need to be able to do some conversions with grams. But if you're able to get the main concept here, you should be okay. All right, so the problem for limiting reactants, they typically look like this, where they've given you 2 different chemicals. I've told you the reaction as well as the amount of those chemicals that you have, and they want to know if these react, which one's going to run out first, the limiting reactant, and then how much of the product will be produced, and how much of excess you have of the other thing, or how much more potential product could you make. There's a ton of ways that they can label that, but that's the main idea. So when you're looking through these types of problems, let's just look at our flowchart. You got to think about, okay, well, what skills do we need? You're going to need to have some dimensional analysis here. You're going to need to be able to work with like molar masses and put them in a larger molecule. Most of the time, they don't give you the molar mass of a larger chemical, but you have to kind of figure it out from your periodic table. And you're going to really need to be able to keep track of your work in this. It's super important to be able to keep track of work while going through this. And so the relevant information is basically, if you think about, they've given you the masses, and they've also essentially told you the grams per mole by giving you these little pieces of information. So that's going to be relevant for what we're doing. And we need to find products and the amount of excess reactant. We're going to need to use conversion factors. So I know that right off the get-go. I need to figure out how much of this reactant can turn into a certain amount of product. I'm not going to draw a picture for this. You can do the bar graphs, but that's more of like how I think through the problem. I do have a mental picture going through like what is what, and I am thinking about something like that bar graph while I'm going through it. And I know what my plan is. I need to take these 2 reactants and figure out how much product they could make and figure out which one's going to be more limiting. And there are other ways to solve this. You can kind of work through it a little bit differently, like a longer path to get to something. You can do in theory. So if we're asked what is the limiting reactant, I typically just try and see how much of product I can make from a given reactant. So I know the 110 grams of the iron, that's going to be pretty easy for me to turn into molecules, or moles I should say. And this is the iron. Yes, I'm going to write it in every single time. And in 1 mole, you have the 55.845 grams. And we can say now that I have moles of the iron, the Fe. I can then turn that into, let's just go with the H2 because they did ask for how much H2 is being produced. So I know what my path is because I might as well work towards part 2. I mean, I could just solve for the iron oxide, but it doesn't really make sense given that they've asked us for that one. So I've got 3 of these moles, and that's going to be for every 2 of these. Okay. And then in 1 mole of H2, we can ask how much that's going to weigh. And it's the 1.008 times 2. I believe that's 2.16. And that should give us the final amount of H2 if we do that calculation. So why don't we go ahead and get the calculator out, and we can do that. I know I love my Wacom tablet. I've got a couple shortcuts on there like that, which are, gosh, they're so good. So actually, hold on. 110 divided by 55.845. This is why you got to write out your work, because sometimes you do the wrong operation and you got to double check and be like, wait, hold on. So this divided by that, and that will get me here. And then times by 3 divided by 2. That should get me about there. And then times that by 2.016. And so I get a final mass of 5.95. So we had 3 sig figs originally. I'm going to just, well, actually, did we only have 2? This is only 2. And that's actually only 1 sig fig. Oh man. Okay. Well, let's say that we only have 2 sig figs and 1 sig fig for these calculations. So we've got, what is that? 5.95. I mean, we're not giving the final answer, but they do want to know how much of the limiting, or how much of it is produced. So I am going to actually limit it. So that 0.9. So it's 5.9, which would be we're going to have to round that up to the 6.0 grams per H2 produced. It's very important that this was what was used, just so that we're thinking through what we have here, and that is going to correspond with what we produced. Okay. And then we can do the same thing. I'm going to just do a different color to show that we're doing the different thing, the different chemical. So we've got 90 grams of H2O. And now we've got grams H2O and 1 mole H2O. So the weight for water is going to be 15.99 plus that times 2. Is it? Yeah. I think it's actually 0.999 plus 1.008 plus 1.008. And so that was 18.105. And then we've got, what is this? This is the moles of H2 now that we're working with, H2O. And then we want to figure out how much H2 we can produce from that. So it should be a 1-to-1 ratio. We could write this as 3/3, but 3/3 is the same thing as 1/1. So I'm just going to simplify that. The equation was 3 and 3 right there. So we knew that for every 3 of these used, we would produce 3 of that. And also we're assuming this is what is used up in this calculation. And we should have the same molar mass because it's the same chemical. And let's see what we get there. We've got 90 divided by, what's that, 18.015. And then we're going to times that by 2. So it's 9.99 grams H2, which we can round. And this was actually only 1 sig fig that we had been given there. So that was that going to be 10? Grams of H2. So if we think about this, it's very useful because now we're saying this was what was produced and that was what was produced when we were given those reactants that were able to be used up completely. Now in reality, we can see, okay, I'm going to run out of the iron first. So we can say for our answer here is limiting reactant. So that's that part 1, right? That right there. And then the part 2, the II, we can say that we're actually only going to produce the 6.0 grams of H2. And then how much excess reactant do we have? Again, a number of ways to solve for this. We can find the difference between what we expected to be produced and was actually produced and say there's that potential for that and go backwards. I'm going to show you a slightly different way because that's, I believe, what we did on the last stage. But if we go here and we just start with, sorry, just give me a second. I want to give myself a little bit more space before the next problem. We start off, and it's going to start off kind of the same. If we start with this used, and we now know that this is what's limiting us, we can say how much could that potentially have reacted with. So in other words, what we're saying is I now know that I've used a certain amount of iron, and I want to know how much water that would react with. So I'm basically saying, okay, I know what this change was. I want to know what that change was, and I'll be able to calculate what's used there in effect. So we've got the moles. Oh, sorry, let's change this. Let's do green. All of the H2O. And then we've got mole of H2O and grams of H2O, which we have earlier from our calculation, which is that 18.015. And when we have 2 of these, how much water are we reacting with? Reacting with 3 water. So we can go through this calculation and we should be able to say what was actually used of that water. So if we do that, we get, what is that? 110 divided by 55.845 times by 3, and then divide that by 2 times that by 18.015. Okay. And so we actually used up the 50, was it 53? 53.2 grams of H2O. I just want to double check. We did have 3 sig figs, or 2 sig figs starting off. So we actually, we're going to give it in our final answer. We'll do the rounding at the very end of the final answer that we're providing. So we had initial minus used gives the amount of excess. And you can think about that like, okay, I had some initial amount, I subtract what I used, and I have some excess left over. That's kind of what we're doing here. The initial amount was 90 grams minus 53.2, and it's like kind of like goes on, I believe, in that. And these were both H2O, right? Yeah, H2O, H2O. Good, so we're subtracting the same thing, and we can get that calculation. So it's 90 minus 53.22, and so it's 36.78 grams H2O, and then we need to actually round that to get the sig fig answer. So we only had, in this place, it was actually only to the, if we're doing subtraction, we were only given the, essentially the tens because we didn't have a decimal point on that. So yeah, we can only say this accurate to the tens place. So we can only say it 40 grams H2O was what was the excess amount. Now, if we had put some decimal points on, I probably should have put some decimal points on here. That would have changed our sig figs a little bit. But the actual numbers that we use in our calculations would stay the same. It's just that certainty that changes. All right, sometimes they give you problems that are kind of all over the place where they've got bits of information that aren't grams or moles, but they might give you like a concentration. So you have to make sure you're working with the right units. So this combines a little bit of dimensional analysis with what we've done so far. So if we looked at the earlier situation where we had this acetic acid and we knew the volume, and then we also had the mass of not the acetic acid but the baking soda right here, we need to figure out which one of those two is our limiting reactant. So to get started with it, this first one is pretty familiar. It's the 6.0 grams, and then it's going to be a pain to write this each and every single time, but I'm proving a point. So we've got that grams, and I'm actually going to, instead of write it out every single time, just copy paste it. So we're trying to figure out from that grams how many moles or weight we're finally making. I'm just going to do it in the grams, not H2. I should have written in a different product. I just copy pasted that over. Let's say how much CO2 will be produced, because that's really what we're looking at, right? So if we've got grams of this stuff and then we want to do moles of it, yet we're just gonna do it like that. In 1 mole, we know that this is going to weigh, this is that baking soda, so this is 84.06 or 0.007. Okay, So we've got the molar mass. You could get this from the periodic table. Sometimes they just give it to you. I'm just providing it to you so that we don't have to do the periodic table with that. Again, I do have a video on how to find molar mass of a chemical from the periodic table and its formula. So we've got the moles of that stuff, and that's going to be then converted into moles of CO2. And then we're going to need to convert that from the moles of the CO2 into grams of CO2. So if we look, our conversion factor for this is going to be a 1-to-1 because you make one of these for every one of those that you use. So that math is easy at least. And then carbon dioxide, I believe this is 12 plus 16 times 2. I'm just going to do a rough estimate for this because that's not really what we're focusing on here. Probably should be a little bit more precise, but given that our number that we're working with only has 2 sig figs, it's probably not a big deal to be a little bit imprecise there. So we've got 6.0 divided by 84.007, and then times that by 44, and we get, what is that, 3.14 grams of CO2. And then it's a little bit more complicated for this other one because they didn't give us grams, they gave us milliliters. And we do have a concentration in moles per liter, so we can use that, but we got to get there first. So we can take let's do a different color just to show that it's a different chemical. We've got 70 milliliters of CH3COOH. And yes, we're going to be copying that over many a times. I know now you're wishing that you had something like this to do this on. So we've got milliliters to liters because we need to go and have something in liters for our next conversion factor. So in 1 liter, there's 1,000 milliliters. And then we've got, what's this, 0.83 mole. And I suppose I should be putting this next to each one of these. And then we can just move this all over. And so that's what this is of. And then we've got our mole of the stuff. And we're converting that into moles of CO2. And in this case, I believe it is also a 1-to-1 ratio from our reaction. This reaction is very simple in terms of moles. That's one of the reasons people really like to work with it. And then it's the same molar mass for carbon dioxide that we used before because we have moles of CO2. So in 1 mole of CO2, that's the 44 grams. And we should get our final answer in grams. And everything, all the units should cancel out. I suppose I should be canceling out my units, right? And this is 1 liter to that. And then that cancels out here, and there, and there, and we're left with just grams. Okay, so let's actually do this calculation. It's 70 divide by 1000 times 0.83. And that's gotten us here. And then there's times 1. We don't need to do anything there. Times 44. Okay, so we got our 2.5. What was that? 2.55 or 2.56. So this one is more limiting here, just barely. They're pretty close to each other though, to be honest. We could probably add a little bit more of the other stuff, but they're fairly close to each other. This was the situation where they should be pretty much reacting. I bet if we went up to the next number, if we did 80 or something, then that would be pretty good. Or it might be a little bit too much. So we've got this, which is our limiting reactant. I'm going to just limit that then, or do our sig figs on that rule. So we were only given something with actually only one sig fig here. Again, 70 without the decimal point would be one sig fig. So yeah, this ends up getting estimated to 3 grams CO2. Anyways, sorry, that looks like a 3. That should be a 2. And I mean, keep in mind, given that this could be off by like quite a bit of milliliters, this answer is going to be fairly inaccurate as well. And so that's probably why these cancel out at the 70 milliliter mark, is if you go too much higher, then it doesn't really make more stuff. And so we figured out how much CO2 is produced, and now we know that this is also our limiting reactant. So that was the aqueous solution. So the vinegar is the limiting reactant. So that's that part 1 here. And then how much CO2 is actually produced. That was this here. And just kind of keeping in mind, this is the produced. And this is how much was used. And then also this was how much was used. And then this is kind of like what could have been produced if we had actually used up all of the all this stuff, but there was a little bit excess. Okay. And then how much excess, we then can do that calculation by just going kind of like this. But instead of CO2 that we're making, it's the other stuff. So maybe I'll turn that into one of my interactive questions. I'll put that in here and have you solve for that and check your answer. Yeah, I'm going to do that. Okay, thank you for joining me. This has been Andrew McLaren. Thank you for McLearning with me. I've got a few more offers that I'd like to let you know about. And remember, like and subscribe. For each video on YouTube, I am making an interactive version using HP5. These will be for sale on Podia. And if you click on the link in the video, you should be able to go directly to that product. I also have 2 demos I'm going to be linking so you can kind of see what these products look like. So I would recommend checking out those demos. I also offer one-on-one remote tutoring through Wyzant. Please use the links that I have linked below. That way I can get 100% of the hourly rate as opposed to 75. Each video also has a link for my Patreon, and you can join at the $3 level to get some resources I use for tutoring or to support the channel. And I also have a $5 raffle level, which you could either get some free online tutoring or 5 interactive lessons for free. You choose which ones. And then I also have my Teachers Pay Teachers, which has some old lessons that I made from when I used to be a teacher. I may be adding to that. Thank you for spending your time with me. I hope that you learned something.